right. So, we live on Earth's crust, right? Earth's crust is solid rock. Now, this solid rock that we live on, it gets beat up all the time. You know, precipitation like rain and snow fall on it. Plants grow on it. Rivers flow on it. It's out there getting beat up by the heat from the sun all the time. And all of this action that happens to the exposed surface, well, it damages the surface. And Earth's crust breaks into small pieces. And we call those small pieces sediments, right? Now, here's the thing. Sometimes those sediments will start to pile up on each other. And especially if they're carried by water, they will go downhill till they find the lowest elevation in their travels, and that's where they'll sit. And they'll deposit right there in that low elevation spot. And as time goes by, more sediments pile up on top of it, and the weight of all that water from what was landing there with the sediments and all the sediments above it starts to squish the bottom sediments, and they squeeze tight together. And any water that was in between those grains of sediment is forced out, or maybe the water will evaporate in different circumstances. And the water that was there, it had minerals in it. And those minerals are left behind as they were dissolved in the water, and now that the water is gone, the minerals are left behind because dissolved minerals can't evaporate or get squeezed away. So what happens is those sediments become like cemented together, and they create this rock A, okay, which is called sedimentary rock, like this sandstone. You can see the different layers of sand were falling, and then the bottom layers got squeezed together first, and the top layers. Okay, and there are whole sections of Earth's crust that are made from this type of rock called sedimentary rock. Okay? But we know that because of tectonic activity, subduction can occur. And if any kind of Earth's crust is subducted underneath the surface and goes deeper into the lithosphere and asthenosphere, it's exposed to extreme amounts of heat and pressure, and it will chemically kind of like cook the rock, like rock B. Rock B is metamorphic rock. Now this rock is basically what happens if crust full of sandstone is subducted. Now, the subduction I'm talking about here is not enough, or it's not deep enough to melt it into liquid magma. Okay, all it's really doing, it's basically like putting sandstone rock into Earth's oven, and it cooks it, bakes it, okay, and it comes out chemically changed, okay, like this quartzite, this metamorphic rock. Now, if subduction were to continue and this went deeper underneath the lithosphere and all the way into the asthenosphere, where the temperatures are hot enough to create melting, well, then we're going to get a whole different story. We're going to get molten material, which can cool and harden in place, or if it erupts through volcanic activity, we can get lava, which can cool and harden on the surface. And anytime you have the molten material cooled and hardened, you get this igneous rock, like this granite you see right here. Okay, rock sample C. So these three rocks all kind of have a relationship. But what's unique about rock sample C is that it's the only one, okay, that is made from cooling and hardened lava and magma. And if you think about it, when Earth first formed, it was a big blob of molten stuff. So it started to cool off. And as it cooled off, the only rock we had on our planet was igneous rock, okay? But then, like I said, some things happened. That crust started getting beaten up into sediments, okay? And then subduction with the tectonic movement started occurring. And we would get some subduction, and we would even get deeper subduction occurring. So all three of these rocks have a relationship.